Okay, so on to question 54. So there's an elaborate looking shape over here, and there's a lot of steps that are kind of unnecessary to tell how this works. Um, for this question, I'm actually gonna mix it up. Like I'm not gonna start a question. I'm not gonna start part A. Um, here, uh, there's two functions we need to know about. We need to know about p sub n, oh, p sub n, and u sub n. And then we are given a sum right here, just and we don't know what this is yet. But you can look and you can spend like 5 seconds and realize this is the sum for p sub 100. And you can look at it because the shaded triangle is 1/4, and then it becomes 1, 2, 3 out of 4, 8, 12, 16 triangles. So then it's 3 out of 16, and you see that just by looking at it, it equals p sub 100. So we're now going to do question B and C. Uh, Knowing that, uh, and we'll do A after B and C. Actually, we'll do E, B, and C at the same time, or E first, then A, then B and C, and then we'll go on to D. So it's going to be interesting. Never had this problem is ordered weirdly, but for this is obviously P. So, and it's obviously a sum with a it's a geometric sequence. So we're gonna do the sigma as n equals 0, and this is goes to 100. Um, but here we're gonna go whatever value we want w. 1/4 times 3 out of 4. Yeah, because yeah, to the w. And I think that's good. I think that's good because 3 out of 4 and 1/4 times 3/4 is 3/16, then 9/64, and it goes on, it goes on. So I think this is a good geometric sequence to provide for P sub W. I can't. Can you see that? Yep, P sub W. Um, Now, oh, I didn't do equal. Now, for you, it should just be the complement. What does the complement? It means? It means that it should fill the fractions that was left behind by the other. So what does that mean? So if I write it out, it would still be the same sigma from n equals 0 to w. And then since it's 1/4, to make it 1, it would be 3/4. I first thought it was 1/4. It's actually 3/4. The same thing as, oh, no, 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 not w, as p. And the reason why is because it's technically p and w are recursively are decreasing together. So it should be the same. It should be the same rate. I don't know why I didn't think. And you could write out the sequence too. You can notice that this is what uh, you start with 3/4, and then you count, and then you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 9/16. 9/16, and then this is another 9/16. So 9/16, and whatever that is, just simplifies to 9/16, which is when it multiplies by 3/4. So it's the same. It's the same pattern. So for u sub. Oh, and we could just get B, C, and E just done really quickly. B would be u to the n would be equal to u to the n minus 1 times 3/4 when u to the 0 equals 3 over 4, and p to the n would equal p to the n minus 1 times 3 over 4 when p sub 0 equals 1 over 4. So now we're going to go to, so that was B and C actually, real quick. That was really easy. We just used the sigma notation. We just converted to sequence notation. Now we're going to do D. Should we do E? No, we're going to go to E, which, again, is very simple. We already wrote down most of the work. So it would be the sequence of W to W, but at this case it's 100, P to the 100, right, which I wrote over here. N equals 0, 1 over 4 times 3 over 4 to the 100. So that's, I think, really simple. And for D, we could solve this. So D, I don't know why I erased that much, is 1 over 4 times 1 minus 3 over 4 to the 100 over 1/4. These cancel. So this is 1 minus 3 over 4 to the 100th. And I need to do this in Desmos. And it's a very small number. This is a really small number. Even Desmos won't round to it. Yeah, it's a big number. It says 1, but take it or leave it. Just can't. You can't round it that. You can't go that high. And then for A, this is, now we're going to go back to what the problems we're supposed to solve. P1 should just be 3 over 16. And I'm just copying. And by the way, I'm just using these numbers right here. I'm not copying from anything else. P1 should be 3 over 16. P2 should be 9 over 64. B3 should be, and this times 3 over 4. So this would be 27 over 4, which is 256. For P, this is the P series. Wow, that's not P series. And for U, it should just be the same series, but starts at 3 over 4. So U1 should just be 9 over 16, then 27 over 256. And then the third series should be 3, 60, 60, 60, 51 over 3, 600, 750, 780. I did that really fast. I need to make sure I'm right. I don't think I'm right. 3, 18, 3, 600, 750, 768. Yeah, that looks more right. And that's for the U series. So hopefully this proves that you can go backwards and do the problems not in order and still get the answer. So yeah. Okay, now on to 57. This is a pure example of a Desmos problem. Some of this stuff you can just figure out intuitively, but please graph it on Desmos. You would find out that the period is 4 pi. And the reason why is because to equal 0, sine of x equals 0, or like according to the ZPP, right, the zero product property, uh, actually, you do not use that. To get the maximum, you need x to equal pi over 4, I'm pretty sure. And then it's every cycle of 4 pi, because if it was every a cycle of 2 pi, I'm pretty sure that it would not be a max, because it would cancel it itself with the cosine function. I don't know if that made sense, but please just graph it on Desmos. You would see it's the same thing. The range is 0.5, is 0.5 to negative 0.5 to 0.5. And the reason why it can't be 1 is because if it was sine of 360, then or sine of, let's just say sine of like 90, right, which is 1. Cosine of 90 is 0, and 1 times 0 is 0. So obviously that's not a max, so it has to max out at some point. And it turns out 0.5 and 0.5 are the answer, right? When the two of, who would have thought that the multiplying 2 of halfway of both numbers equals the biggest number. That's a maximum and minimum like trick that we'll go over soon. And is the function sinusoidal, and the function is sinusoidal. And I don't know how you want to write this. I'm basically just gonna say there's nothing in this function that will make it not sinusoidal. Um, like there's no inverse sine, no inverse cosine, no anything to stop that sine x and cosine x, because cosine x is just a function of sine x, right? It's sine x plus pi over 2. And so there's nothing stopping sine of x from being not being sine of x in this question. So I think this question is pretty easy. We can move on. Okay, so on to 58. Here we get to see exactly what the last question was trying to was never mind. I don't know what I was gonna say. But obviously, when you see inverse sine and or inverse of a function and a normal of a function, then you know it cancels out. But we've seen from previous problems that that's not how it works. So with trig functions, because there's a range and a domain of inverse um, functions. Um, but yeah, let's just go into it. Sine of inverse sine of 0.32. These are degrees. Um, Sine of 0.32. If that's 0.32, the ratio, um, the inverse sine of that should be in the first quadrant. So the sine of that should equal 0.32. Inverse sine of 1.61. That's definitely the first. The first is definitely in the first quadrant. So the tangent of that should be the same. Cosine of 123 is in the second quadrant. However, if you inverse cosine it, it's the first. The only way that you can get a negative number is by going 123 degrees. So like if you, this is 77 degrees, right? Because this is 123. Wow, I freaking messed that up. This is 57 degrees. Um, when it projects onto the x-axis, there's no other way. Like there's no that's the most efficient way for inverse cosine to describe it. So it would still be the same. It would still be 123. However, for sine of 137, I'm not gonna draw it, or maybe I will. It's like this. This sine value right here has the same sine value here, and for the inverse sine function, that's more efficient. That's more efficient for it to graph. So this should be 43 degrees. Or I'm just gonna write 43. I'm not gonna deal with units. So that's it. All right, on to the last question. Question 59. It's about Courtney running laps. Um, to anybody who knows Mr. Spence, yeah. Miss him. He was my math teacher last year. Anyways, Courtney has an 8% chance of stopping running, but 92% chance it's going to keep going. And the question's asking to give two justifications for the equation to equal 1. The first justification is a complete philosophical one. There's 100% chance that Courtney will do an action. So there is, right, because 1 is 100%. There is 100% chance that Courtney will either stop running, or run. Like there's no other option, right? It has to be 100%. Um, you could also say it's a converging sequence, but as like proof of the proof. But that I'm just gonna stick it as that. There's no other way you can say it, right? It has to be 100%. It cannot be not 100% because then we'll be dealing with continuity issues. Um, but for the second one, we're proving it. As you can see, the sequence has a ratio of 0.92. You can see it's getting exponentialized, and 0.08 is the constant. So what does that mean? We use the infinite geometric series formula, which is a over 1 minus r. So it's 0.08 over 1 minus, and since the rate is 0.92, we do 1 minus 0.92. This is obviously 0.08, and this equals 1. I think this is a really cool problem, really easy as well, and let's go on to tomorrow.